Okay, so next speaker is Simon Vialaret from Bochum and Orsay, who will talk about systolic inequalities for S1-invariant contact forms in dimension 3.
Okay, thank you very much. And thanks a lot for the invitation. I'm very happy to talk here. So I'm going to talk about some aspects of contact dynamics. So dynamics of Reeb flows in dimension 3. And I will start with a definition. So whenever we have a contact form, we can consider its Reeb flow. And Reeb flows are a class of flow that are expected to always have, at least on compact manifold, a periodic orbit. So that's the Weinstein conjecture in dimension 3. It's a theorem of Taus. But okay, for all the situations we consider today, it's very easy to produce periodic orbits. So existence of periodic orbits are not going to be a problem for us. And okay, whenever we can look at the collection of periodic orbits, look at their periods, and we will call systole of a contact form the shortest period of a closed Reeb orbit. Okay, so that's a number which describes, let's say, some aspect of the dynamic of the Reeb flow. And we will say that a class of contact forms, so by class of contact form, I just mean a subset of the set of all contact forms on some given manifold. So we say that a class of contact forms satisfies a systolic inequality whenever there is a constant depending on this set, such that for all contact forms in this class, the systole of this contact form to the right power, so in dimension 2n+1, we look at the systole to the n+1, is less than this constant and the volume. So imagine that we normalize our contact form so that it has volume 1. Then this kind of statement says that there exists, that all Reeb flows, let's say, all contact forms in the given class admit a periodic orbit with period uniformly bounded. So it's for a class of contact form to satisfy a systolic inequality, it's a statement about existence of short periodic orbits. Okay. And I'm going to state some, the point of today is to give some situations in which we have systolic inequalities. And first, let me say a few words about motivations. So one first important motivation to study this is the fact that those questions arise from, they come from metric, let's say, Riemannian and Finsler geometry. So we can say that a closed manifold satisfies a systolic inequality whenever for all Riemannian metric on it, there exists a short closed geodesic in the same sense. And this, understanding whether or not a given closed manifold satisfies systolic inequality, it has been quite studied. It's still very much open, but there are also some kind of rather general results about this. For example, there is a theorem of Gromov, which says that there is a big class of manifolds which are called essential, which all satisfy systolic inequalities. Okay, that's the first motivation. It's an interesting question in metric geometry, so why not studying it also in the contact setting? Another motivation, which is more symplectic, comes from the relation between the systole and symplectic capacities of convex domains in R2n. So it is an important fact that for many symplectic capacities, we know that when we evaluate them on convex domains in R2n, the number that we get coincide with the systole of the boundary of this domain. So convex domains have contact type boundary. So the boundary carries a Reeb flow, and there is a systole corresponding to it. And for many symplectic capacities, the capacity of the convex coincide with the systole of the boundaries. And there is a very influential question asked by Claude Viterbo, which asked, let's say, whether or not a certain inequality involving symplectic capacities of convex domains and the Euclidean volume of those domains. So whether or not such a certain inequality holds for all convex domains, this we know that it's not true since work of Chaim Kislev and Ostrover, or at least for some relevant class of convex domains, let's say. And for all those capacities that agree with the systole, well, this inequality takes the form of a systolic inequality. So that's two reasons, let's say, why we would like to prove systolic inequalities the contact, in the contact setting. So let me tell you a few things that we know. So first, we know that there is no global systolic inequality. So it's a theorem of Abodandolo, Bramham, Rinevich, and Salomao in dimension 3, and of Murat Salam in higher dimensions, which says the following thing, that the class of all contact forms on any given contact manifold does not satisfy any systolic inequality. So more precisely, take M psi, your favorite contact manifold, take epsilon, any arbitrary small number, you will be able to construct a contact form on M adapted to this contact structure, which has volume less than your epsilon and systole always larger than 1. So there is no global phenomenon of existence of, let's say, forced existence of short Reeb orbits in general. That's one, let's say, one good place to start. Another result that I want to mention, because it allows me to, because then I can define a certain class of contact forms, is the local study of the systole in the neighborhood of some special contact forms that are called Sol. So we say that a contact form is Sol whenever all of its Reeb orbits are periodic and have same minimal period. So one easy example is take the round metric on S2, and its geodesic flow is going to be the Reeb flow of a Sol contact form. And it's a mix of a theorem of Alvarez, Paiva, and Balazs, and of Abodandolo and Benedetti, that Sol contact forms are exactly the local maximizers of what we call the systolic ratio. So the ratio of the systole to the right power by the contact volume. So what does it mean? So first, the result of Alvarez, Paiva, and Balazs says that any such local maximizer has to be Sol. And the other, conversely, Abodandolo and Benedetti proved that if you take a perturbation of Sol contact form, then you all with fixed volume, let's say, then you always create a periodic orbit that whose period is smaller than the period of the Sol Reeb flow. Okay, so that's the state of the art. Let's say there is no global systolic inequality. There are also, but okay, the local behavior of the systolic ratio is also understood in some situations. And today, what I want to state is what we could call, let's say, a semi-global systolic inequality. So let me now move to the setting. So we will consider, we will work in dimension 3, and the family of manifolds that we will consider are total spaces of S1 principal bundles over surfaces. So for the notation, for G and E two integers, we will write MGE for the total space of the unique S1 principal bundle with Euler number E over some oriented surface with genus G. Okay, so that's another way to see those manifolds is just a closed free manifold endowed with a free action of the circle on it. And we're going to look at invariant contact forms. And a contact form is said to be invariant whenever it is invariant, meaning that we pull it back by the flow of the action and we get the same thing. Another way to write it is that the Lie derivative of the contact form in the direction given by the action is 0. Okay. And we're going to give a name to the space of all invariant contact forms on a given manifold. So omega GE will be the set of positive invariant contact forms on this total space of the principal bundle, MGE. And here positive means that the orientation coming induced by the contact form alpha, so the orientation given by the contact volume, coincides. We have the orientation of M as an S1 principal bundle over an oriented surface. So the two orientations coincide. So this space, we kind of know, let's say, what it looks like. There is an old paper by Lutz in which he classifies S1 invariant contact structures in dimension 3. And for us, let's say that, okay, so he fully describes, let's say, the infinitely many connected components of this space. Each of them has some nice combinatorial description. And for us, let's say, let's just keep in mind that it is kind of a big space, meaning that we can always have invariant contact forms that are arbitrarily far from anything convex or anything Riemannian, let's say. So, Okay, so that's the class of contact forms that I'm going to consider. S1-invariant contact forms on some manifolds and done with a free S1 action. And now I'm going to state the first result, which is the fact that almost all, let's say, invariant contact forms satisfy a systolic inequality. So the statement is the following, that there is some universal constant, it's really just a number, doesn't depend on anything, such that for all choices of genus and for all non-zero Euler number, then, well, for all invariant contact forms on the corresponding manifold, on the corresponding principal bundle, the square of the systole of the contact forms is less than this constant times the volume. Okay, so it's a global systolic inequality that holds for all invariant contact forms on non-trivial principal bundles. Okay, so let's make a few comments about this. First, we can weaken a bit this assumption of being invariant under a free S1 action. We can allow, let's say, almost free S1 action, so meaning that we can allow the presence of a finite number of singular orbits. So let's say a finite number of orbits with finite but non-trivial stabilizer. And the family of manifold that you get are Seifert bundles. And okay, we get a similar statement for Seifert bundles with non-zero Euler number. But we cannot weaken too much this assumption of being invariant under an S1 action. For example, asking invariance under just a finite group action is not enough. What does it mean? It means that on S3, for example, you can construct contact forms that are invariant under some zk action with k arbitrarily large that have arbitrarily large systolic ratio. Okay, so in that sense, okay, it is important to have this S1 symmetry. Of course, okay, this statement is only valid on non-trivial principal bundles. It's a very natural question to know what happens otherwise. And it's the only interesting thing that I can say is that it's really not here. And the proof definitely uses, I'm going to talk a bit about the proof a bit later. The proof definitely uses the non-triviality of the bundle. And it is an important argument, let's say. So, okay, I don't know what happens on S1 times S2, for example, or on T3, this I don't know. But okay, that's life. Last thing, okay, that's a pretty general inequality that is valid for a big class of contact forms, but then the downside is that it's not sharp. I don't know what should be the best constant that we can put there. But okay, we can also make some further assumptions to get a sharp inequality. So what are those? We're gonna know for the second statement, we're gonna assume that the contact forms are tight. So in contact topology, there is a dichotomy between tight and over-twisted contact structures. And in this one, I only consider the tight ones, and I will tell you why a bit later. And we also consider for this second statement bundles over the sphere, so genus 0. So the statement is the following. There are two cases. If the Euler number is negative or equals to 1 or 2, then for all invariant tight contact forms on this, again, on the principal bundle of Euler number E, the square of the systole is less than 1 over E times the volume. So E is still the Euler number. And equality holds if and only if alpha is Sol. Okay, so that's not so surprising that equality holds exactly for Sol contact forms, given the result of that I stated before of Alvarez Paiva, Balashov, Albonandolo, Benedetti. So that's the first case. The second case, well, for E larger than 2, then the behavior is slightly different. We still have a systolic inequality, which with this one, this time constant 1/2, and equality is never reached, and the constant 1/2 is optimal. And by optimal, I mean that there is a sequence of contact forms in this space, such that the ratio, the square of the systole by volume, sorry, tends to 1/2. Okay, that's the second statement, so sharp inequality for tight invariant contact forms on bundles over S2. And now I'm going to move I'm just going to give a small sketch of proof for both theorems, and then I will be done. So the first step of the proof is to produce some nice surfaces of section. And by nice, I mean S1-invariant, so invariant under the action. So what is a surface of section? Well, when I have a flow, let's say, in a free manifold, a surface of section for this flow is going to be an embedded surface, possibly with boundary. That has the following property that when I take a point on this surface and I follow its orbit by the flow, then I will hit this surface again in the future. So it's a way. So in general, it's not easy at all, given some flow, to produce a surface of section for this flow. But once you have them, it's very convenient because it reduces the dimension of your problem. So here, the S1 invariance of everything actually allows you to produce some very nice surface of section. So first, having a surface of section at hand reduces the dimension by 1, but the surface of section being S1 invariant, it actually reduces the freedom, let's say, the dynamic of, say, most of the dynamic of the three-dimensional flow to a one-dimensional problem. Okay, and this surface of section is not going to be global. It's not going to see the whole flow, but enough of it, let's say. And it's not going to be connected in general. It's going to be a finite union of embedded cylinders in the free manifold. So that's the first step, finding those nice surfaces of section. And now, in the case of theorem B, so under those assumptions of tight plus bundles over the sphere, this actually forces the surface of section to be connected. And then we only have one surface of section. We only have, everything is encoded in one real-valued function, let's say, and there is a direct argument to get the systolic inequality. So that's convenient. Then for theorem A, it's less direct. We cannot assume that, I mean, it is not going to be true that this surface of section is going to be connected. It's going to have a certain number of components that we can control, but still, it's not clear how everything interacts together. But we can argue by contradiction and assume that we can find invariant contact forms with arbitrarily large systolic ratio. So now the technical part of the proof, let's say, is the following, is that we prove that if you have such a contact form with large enough systolic ratio, then this actually forces the first return map on each component of the surface of section to be close in a controlled way to a uniform rotation of the cylinder. So that's why not, I mean, in principle. But now the contradiction comes from the fact that you can also compute directly the Euler number of the bundle from this surface of section. And the only value for the Euler number that is going to be compatible with this property of return maps being arbitrarily close to uniform rotation is going to be 0. So if you assumed in the first place that you were working on a non-trivial principal bundle, then this number is actually not 0 and you get your contradiction. And that's it for today. Thank you very much for your attention.
Thank you very much. Are there questions or comments or remarks? Could you say a little bit more about the surfaces of section, what they look like, how they are found, maybe in some simple example?
Yes. So in general, I mean, what you can do is the following. So you start with any invariant contact form. Being invariant under this S1 action, well, you have a moment map associated to it. The moment map descends to a map from the base of the bundle to R. It's a real valued function. And now you can take, essentially what you can do is taking a curve that is transverse, a curve in your base, in your surface, that is transverse to level set of this moment map, and take the pre-image of this curve to the total space of the bundle. So this curve is just going to be a curve in your base, and the pre-image will be diffeomorphic to a cylinder. And you can check directly that by looking at, let's say, how the Reeb flows projects on the base, that this is going to be a surface of section.
But how do you have a curve transverse to the levels of a function?
Well, I mean, take the base S2, let's say, and imagine that your moment map only has 2 critical points.
Yes.
Yeah. Now you're going to remove those 2 critical points from S2. You get something that is a cylinder, and you take a curve, a path from the top to the bottom, staying transverse to the level sets.
So you have to remove, yeah, but you have to remove points.
Yes, yeah.
And how do you see that you only have one connected component in on the sphere? Is that the
yes
case?
So in general, let's say I mean, by one connected component, I mean one useful, let's say, connected component. So okay, so let me say 2 more words about that. So first, when you have your invariant contact structure, let's say you have a set of you have the 0 set of the moment map. This corresponds to Legendre S1 orbits. And that's the part that classifies, let's say, your S1 invariant contact structure. So this set under this assumption of tight plus over S2 is going to be connected. And now, let's say the useful part of this surface of section is going to be the when this path, let's say, intersects the 0 level set of the moment map.
Is that related to some Giroux convexity or something like that, or has nothing to do? Having only one connected component.
I mean, yes. So yes. I mean, that's. I mean, let's say the fact that tight implies one connected component. Yes, it's proved. I mean, it's a result of Giroux, let's say.
Okay. Thank you very much.
But then, yeah, it's not really about convexity in the first place, I would say.
Okay. Any other question? Okay, if not, let's go to the next talk.